extremas of the following function? That is a good question to ask. There is an algorithm to find maximas and minimas of this function. And the algorithm or the recipe is as follows. The first thing you need to do is you need to compute f prime of x. And the second thing you need to do is to find the roots of this f prime of x that you've just found. And so that is what we are going to do now. And you can, of course, pause the video and try to do it yourself. So here we just have polynomials. So the only thing I'll need is the power rule. So I bring down the power and I take away 1 from it. So it's 1 over 3 times 3, x to the 3 minus 1, minus 7 over 2 times 2, x 2 minus 1, plus 10 times 1, x to the 1 minus 1, plus 13. Now I am showing work for you. You do not need to show your work. And this is going to be 2, it's going to be 1, it's going to be 0. So it's just multiplying by 1. And this is 1 and that is 1. So I might as well just remove it. And then what's the derivative of 13? It's a constant, so it doesn't have a derivative. So remember that the derivative is just the rate of change. And so a constant doesn't really have any such rate of change. I hope you don't mind if I remove this 1 here. X to the 1 is still x. And if I want to simplify this, maybe I will cancel out the third with 3, cancel out the 2 with half. And then I would get x squared minus 7x plus 10. So I've done the first step, which is to find the derivative of this f of x. So we're halfway there into finding the extrema. But we're not halfway through the question, because for this very specific question, we still need to figure out which extremas are maximas and which extremas are minimas. But already this is very good progress. I now have my f prime of x. So now I set my, or I let my f prime of x be equal to 0. Then this is equal to 0. And then I can write this as x minus a, x minus b. And now I just need to find a and b. So in that case, a will be minus 5 and b will be minus 2. No, a will be 5 and a will be 2. That's x. So this is what I mean. A will be minus 5 and b will be minus 2. You can of course factorize this. You can also use the quadratic formula if you really want to find the roots and you don't know any other way to find them. You can check that this is true by distributing the terms and confirming that this will give you and the equivalent expression. Okay, so x minus 5, x minus 2 is equal to 0, then probably x1, x is equal to 5, or x is equal to 2. Now I'll give them some names. So I'll call the first extrema 5, and I'll call the second extrema 2. I hope that's okay. They're just names. So that's the second thing I've done now. So I have my extremas. So this is there, this is very nice. But then I still need to determine whether these points are maximas or minimas. For this, there's something that we can do. There's a theorem that links the behavior of the derivative with the behavior of the function itself. So here I have 2, x is equal to 2. So this is an x-axis. And here I have x is equal to 5. And if I want to be more specific, so the behavior I'm talking about is if the derivative is positive on a certain interval, then the function is increasing. If it's negative on the same interval, for example, or a different one, then the function is decreasing. Okay, maybe we can worry about the theorem in a couple of moments. Let's just analyze the behavior of the derivative function f prime of x, which is also this one. So what happens if when I plug in any number that's between 2 and 5? Say I plug in 3, then I plug in 3 here. The computation itself is not important. What I only care about is the sign. I know here that the derivative is equal to 0, and here it is equal to 0. But I want to know what's happening in the middle. Is it positive? Is it negative? And this is not difficult to see. So 3 minus 5 is a negative value, and 3 minus 2 is a positive value. So probably this is negative. Okay, what if I choose a number less than 2? What's your favorite number less than 2? It's 0. 0 minus 5, 0 minus 2. This is negative, but this is also negative. So probably the first derivative is positive for values less than 2. X values, of course. And you can check yourself that if you plug in a bigger number, you'll get and that it will be positive. Now, to link this with this theorem that I've been talking about, it just says that if the derivative is positive on this interval from minus infinity until 2, then f is increasing. So this is our f, it's increasing. Same thing here, it's increasing. And vice versa. So because the derivative is negative, then our function is actually decreasing. Because the derivative is negative. That's what our theorem tells us. So here's the catch. If the function keeps increasing before 2, and then it stops at 2, and then it goes down, then 2 is probably a maxima, right? Because it keeps increasing until it reaches the point where x is equal to 2, and then it starts decreasing. Then probably it's a maxima. With the same logic, this is probably a minima. At least intuitively, if we just look at the graph, it's decreasing and then it starts increasing. So at this point of change, it's reached the lowest point it can reach, and then it starts to change upwards. So from here, yes, we can say that the maximas are just 2, and the minimas the maximas of f and the minimas of f are 5. But I also have another way to check this. So let's say you don't like this analysis part, which we perform right now, and you would like to use another test. So for this purpose, there is something called the second derivative test. And the second derivative test tells you that if x is an extrema of f, and now we know that these are extremas, f5 and 2, then if you plug in the extrema inside of the second derivative and you get a positive value, then this x is probably a minima. And the opposite is true. So if you plug in x in the second derivative and it's negative, then probably x is a maximum. That was a typo. But I'm glad I was able to spot it. So let us actually apply this test, just for the sake of applying it. Just giving you different machinery to be able to solve this problem. So we know this is the first derivative. The second derivative will be the derivative of the first derivative. I hope that is not too difficult to follow. So I would differentiate this function. I'll get 2x minus 7. And now if I look at f double prime of 2, I will get something. And if I look at f double prime of 5, I'll get something. Now, f double prime of 2 is 4 minus 7, so minus 3. And by our theorem, if it's negative, then it's a maxima. And similarly, you get 5 times 2, so 10, minus 7, which is 3, which is greater than 0, so it's positive. So this means that 5 is a minima. So not only in one way we have solved this problem, we solved it in 2 different ways. You're of course free to choose whichever way you like to use. This way is nice because you can link the behavior of the first derivative to the maximas and minimas without having to reach out to the second derivative. Sometimes the second derivative is difficult to compute, and so in that case you would like to use this method. But then sometimes the second derivative is easy to compute. For example, the second derivative is just a negative number, so let's say minus 2, and then you would know that all your values are just maximas, because the function, which is the second derivative, is always negative. But anyway, this is just some hand waving. This is how you solve the problem, and these are 2 different ways to attack it.